We've talked about correlation and how correlation just means that as one variable changes, the other changes in a predictable way. And this doesn't mean that one causes the other, just that there is this correlation, this relationship. Specifically, in this class, we're talking about linear correlation. Which is that as one variable changes, the other changes in a linear way. So basically when we graph our points, it's basically forming a line, not any sort of weirdo funky curve. And in statistics, we want to be able to assign a specific number to this. So if we have something like this is called a positive correlation. So a positive correlation would be something that looks like this. This is x, this is y. As y increases, whoops, normally we go the other way, as x increases, y increases. Whereas a negative correlation does the opposite. As x increases, y decreases. And we can actually measure this with a specific number. This number is called the correlation coefficient. And it has the letter R. And the strength of the linear correlation doesn't measure the slope of the line or anything like that. It just measures how closely the points cluster to a line drawn through them. So the stronger that a correlation is, the more accurately we can predict the value of one variable if we know the value of the other variable. So let's say this describes how closely the points on the scatter plot are to being on a line. We would say how closely the points cluster to the line. That would be the language for it. So we've got a couple of options for what this can be. We have a perfect positive correlation, and that would be something like this. All the dots are exactly in a line, or as close as I can get to them. And it could be a steep line, it could be a shallow line. But this has an R of 1. On the other hand, and leave yourself a little bit of room here, on the other end of the spectrum, we could have a perfect negative correlation. Remember, positive just means that as x gets bigger, y gets bigger, so there's a positive slope. Here, perfect negative correlation They're exactly in a line, but they're going downward. And again, that can be either a steep slope or a shallow slope, as long as it's a negative slope. The correlation coefficient in that case equals -1. Right in the middle here, there's no linear correlation. And that could be something like this. Basically, that just if we draw a line, it isn't going up or it isn't going down. There really doesn't seem like there's a line at all. The variables don't seem related. It could also be something like this, where there's clearly a relationship between the variables, but it's not a line. And in between these two, there are different levels of correlation. So we could have a high or a strong positive correlation. We could have a medium or moderate. And we could have a low or weak positive correlation. And those kind of look the way you might expect them to. Here the points aren't exactly on a straight line, they're just sort of a little bit off, but they're still pretty strongly going there. Medium or moderate, there would be a little bit more sort of spread around. And a low or a weak one, there's a linear relationship there. But it's not all that easy to see. And there's going to be some debate about whether or not something is a high or strong correlation, medium, moderate, all that kind of thing. You're just going to have to estimate. I mean, this is clearly perfect, this is clearly no, but the other ones are going to be somewhere in the middle. And this is generally going to be somewhere between R is going to be, maybe somewhere between 0.5 and 1. R is maybe somewhere between 0.3 and 0.5. And low or weak, probably between about 0.1 and 0.3. No linear correlation. R is going to equal 0. The same thing applies for the negative correlation. So we could have a low, a medium, or a high negative correlation. And again, these look very similar to the ones above, it's just they're going in the opposite direction. So this is almost perfect, there's just a few dots on either side. There's a little more sort of variation. Here we can see the relationship, but it's pretty weak. The values for R would basically be what we saw above, just negative. Actually, that should be smallest number on the left. And there we go. So let's look at some graphs. Does each scatter plot show a positive or negative correlation? I really should say none. That's a possibility as well. And is it a strong, moderate, or weak correlation? So here we can see that if we were to draw a line through this one, it's sloping down, so it would be a negative correlation. And that's kind of clustered to the line, so probably say moderate. If you'd said weak or strong, I mean, there's probably a case to be made, but probably kind of in the middle. Here, this is sloping upward, so it's positive correlation, and the dots are really close to the line, so this would be a strong positive correlation. And here, there really isn't a line. Or if there was one, it'd kind of be sort of like flat through there. So we would say there is no linear correlation. And let's interpret some of these as well. Say a scenario, if X is shoe size and Y is height, interpret each R. Let's start off with, say, negative 0.2. This is negative, so this means as shoe size gets bigger, height gets shorter. Remember, negative means as one goes up and gets bigger, the other goes down. However, this is a pretty weak correlation. So we're saying is that knowing shoe size doesn't help us predict height very well. We can still generally say as shoe size gets bigger, height's going to get smaller, but it's not very tightly clustered to this line. If we know that X is this value, Y could still be a whole bunch of different values. Let's say R equals instead that R equals 0.8. Well, this is a positive correlation. Why don't I label how we know? So this is negative. And this part is weak. So this part, as shoe size gets bigger, height gets shorter, that's the negative correlation part. Doesn't help us predict height very well, that's the weak part. This, remember, is a strong positive correlation, just like this. So as shoe size gets bigger, height gets taller. That's the positive correlation part. The fact that it's a strong correlation, it's 0.8, means knowing shoe size lets us predict height well. And if we had an R of 0.1, or excuse me, an R of 1, that's a perfect positive correlation. That means if we know shoe size, then we know exact height. There's no variation. Whereas on the other hand, if R equals 0, There's no linear relationship between shoe size and height. So the correlation coefficient lets us tell whether or not there's a positive relationship. As one gets bigger, the other gets bigger, and how well one variable predicts the other. And we can actually quantify that a little bit further using what's called the coefficient of determination. And that is R squared. R squared is the percent of variation in Y that is explained by its relationship with X. So for example, let's say that R equals 0.866, say if, then R squared literally equals R squared, or about 0.75. This means 75%, so that 0.75 just written as a percent, of the variation in height is explained by variation in shoe size. And what that's really saying is it's saying that if we know somebody's height, then that lets us predict their, if we know someone's shoe size, that lets us predict their height pretty accurately. It's saying that we know there are all these different heights that people have, but if we know their shoe size, then there's a lot less variation to play around with. It's like 75% of their variation in height is sort of taken out if we were to take out those shoe size differences. So that means that these are clustering pretty closely to the line, kind of like we say here, that if I know that, okay, this is the value for shoe size, then the heights are pretty tightly clustered together. And so this is why this is fairly useful, because it sort of tells us if we're taking a whole bunch of variables and trying to use them to explain people's height, like nutrition and shoe size and a whole bunch of other different variables, it basically means that, okay, we know that shoe size explains a lot of the differences between people. We only have about 25% of the data that we need to find another explanation for.